Then after the topic that is physical significance of dipoles. Now see, we can observe some molecules for which the centers of positive and negative charges are at the same place, or we can say coinciding each other. See here, CO2. So the structure of CO2 is such that the centers of positive and negative charges coincide. These type of molecules are called non-polar molecules. So they does not possess permanent electric dipole moment. But no doubt, in the presence of electric field, the dipole moment is induced in it. But some molecules are such that for which the centers of positive and negative charges are separated by some finite distance. It implies that such molecules possess permanent dipole moment, whether the electric field is present or not. So, see here, the example is given to you, H2O. So for that also, the centers of positive and negative charges are separated by some finite distance. So we can say it possesses permanent dipole moment. Such molecules are called polar molecules. And now here we can observe very interesting behavior, very interesting phenomena in the presence and absence of electric field related to these molecules. So when these molecules are in the electric field, then the behavior, that is interesting one. So all these things we have to study, and therefore this concept of dipole moment and its electric field, that is very important thing. Clear to all of you? Then after illustration number 1.10, two charges plus or minus 10 microcoulomb are placed 5 millimeter apart. Determine the electric field at a point P on the axis of the dipole 15 centimeter away from its center O on the side of the positive charge as shown in the figure A, and B, a point Q 15 centimeter away from O on a line passing through O and normal to the axis of the dipole as shown in figure B. Okay. Now see here, see the figure in text, but here the calculations carried out in text are lengthy one, so you have to follow it. Say, suppose first we think about the given data. So magnitude of the charge, that is 10 microcoulomb, so that is 10 into 10 raised to minus 6 coulomb. Now R, that is 15 centimeter, so 15 into 10 raised to minus 2 meter. Then A, say the dipole that is with length we can say 5 millimeter, it implies that from center each charge is at 2.5 millimeter. So A, that is 2.5 millimeter, so that is 2.5 into 10 raised to minus 3 meter. So we can write that is 0.25 into 10 raised to minus 2 meter. Now on the axis of the dipole, we can write the equation of electric field, that is K Q 4A R upon R square minus A square whole square. This we already discussed in the previous theory. So now direct substitute the values. K, that is 9 into 10 raised to 9. Q, that is 10 raised to minus 5, this one. Then 4A, that is 0.25 into 10 raised to minus 2. R, that is 15 into 10 raised to minus 2 divided by this R square. So 15 into 10 raised to minus 2 whole square. And minus 0.25 into 10 raised to minus 2 whole square and square of entire this one. Then solve, you will get the answer. Clear? Then if we consider here A that is very much less than R, then simply you can use the equation K4QA upon R cube. Again here substitute the values of K, Q, A and RQ and solve this one. You will get these two answers nearly equal. Similarly, on the equatorial line, we can use the equation E equator, that is K2QA upon R square plus A square raised to 3 by 2. Now substitute the values of K, Q, A, R and A here and then solve it. Then after, by considering A very much less than R, we can use this equation K to QA upon R cube, and again if we substitute the values of K, Q, A and R and then solve it, you will get the answer. And now we can compare these two will be nearly equal. It implies that by calculation here it is represented if R is very much greater than A, in that particular case, we can use this particular equation directly. So that is just represented here. Okay. But see, in text, this one is calculated like that. First due to positive charge, then due to negative charge, and then after taking the summation, the resultant field. But in theory, directly we derived this equation, and this equation is valid for this one and this one. That is valid for any point situated at any distance. Clear? So directly we can use it. And these two equations, this one and this one, are special cases. And here compared to this 15 centimeter, 2.5 millimeter, that is very, very small. So we can neglect it, and then it is represented here by calculations. Yes, we can use in this type of cases this special case equation also. And then we can check this thing. If we take the ratio of E axis upon E equator, then it will come to 2. Because here the point is at the same distance on axis as well as on equator. Clear?